Hey, it's Mr. K doing a video for AP Physics 2. We're going to look at a little bit of electrodynamics. But before we do that, let's talk a little bit about Gauss's law. Gauss's law, Mr. Gauss, that's his name, so I guess Gauss's law would be appropriate, says that if you have a certain amount of flux, which in this case would be from an electric field, through an area, that should be equal to the charge that we enclose, or that is causing that flux, divided by this thing that we call epsilon naught, or the permittivity of free space. Now, this permittivity of free space is going to change depending upon your material, but if you just talk about vacuum, just space, then it's going to be epsilon naught. I forget the number, but what this is going to turn into is going to be the value k, and you'll see that shortly. So here's the problem. We're going to use Gauss's law to kind of solve that, but what we have here is our two conducting spheres. One is twice the radius of the other. And we're going to plop down some amount of charge Q on this sphere. And this charge Q, if you think about it, if I place down a charge over here, if I were to place down another charge right next to it, that charge would drift over and pop over here. And I'm using positive charges. I understand electrons are probably more appropriate, but let's just go with positive for now. So if I put a positive charge here, there's probably going to need another charge that wants to go all the way as far away from it as you can. And if I put another charge right here, then that's going to try to drift as far away from these two and push them into more of a triangular pattern. And as you try to put down more and more charge in this thing, they want to try to spread out as evenly as they can possibly be, such that they're all pushing on each other equally, such that they just come, they come to a nice equilibrium on the surface of the sphere. Realize that that means that there shouldn't be any net charge on the inside of the sphere of this conductor. All of it should be on the surface because it wants to get as far away from each other as possible. So this is going to be of radius, let's call that a big R. This guy's going to be of radius, let's call that little r, and little r is going to be about half the size, according to the squares that I've used, of the big R. And so if we look at Gauss's law, all this charge, we can consider it to be like focused at the center. If we wanted to, we can do that. We can make this imaginary surface called a Gaussian surface, which would be a sphere in this case. And we would enclose this charge with this imaginary surface that would be a sphere. And so the electric field going through that sphere would be going through this area A. So the area of a sphere would be 4 pi r squared. Okay, so 4 pi r squared is going to be the area of that sphere, and that should equal the charge that we are enclosing divided by this epsilon naught. So we're going to make this r the same r as the radius of the sphere. We're going to bring it in. So we want the strength of the electric field right at the surface. And so this r becomes big R, and we're going to notice that the electric field here, keep that little vector sign on there, is equal to Q divided by 4 pi r squared epsilon naught. And it turns out if you actually find the number for epsilon naught and you plug it in, you 1 over 4 pi epsilon naught, that turns into the value of k, right? And k is 9 times 10 to the 9th. So easy enough, we're just replace 4 pi epsilon naught, these constants, and 1 over, with the value of k. So k, q over r squared, and we're going to use big R for right now. So that would be the strength of the electric field on the surface here. Another thing we can talk about would be voltage. Voltage would be the electric field times the distance. And so if we consider all this charge to be focused at the center, we're about this distance r away from it. So ED should equal the voltage at a particular spot, and that's just going to be K Q divided by R in this case. So keep that in mind. We'll go ahead and keep on going. Here we have, again, the conductive sphere on the left. We have a conductive sphere on the right. We're going to attach a conductive metal wire to go between these two, and we're going to consider this to be very far away. This is a classic physics problem. And when we do that, a lot of this charge is going to want to flow to the right because there is a difference in potential. Here we have zero potential, and here we have some potential, and some potential is more than zero potential. So we're going to want, this charge is going to want to flow away towards the sphere over here. And as it collects, we're going to lose charge from the left side, we're going to gain charge on the right side, but the charge on the right side will be equally spaced out. And it's going to keep on gathering until the forces that are between these charges are the same and equaled out which would be the same as this over here. As we are losing charge, you're going to have this equal distribution of charge on the left side and right side. And the secret here is that the voltage of the left should be equal to the voltage of the right by the time this charge has stopped flowing and going from the big sphere to the small sphere. All right, and so what that means is, if we look at our voltage equation for the left side would be K, Q, let's put a 1 there because that's whatever Q is on the left side, over R should be equal to K, Q2 over little r. All right, and these K's would cancel out. Again, K is this 1 over 4 pi epsilon naught. So Q1 over big R should be equal to Q2 over little r. And so that ratio should hold true. And again, this is considering that these two conductive spheres are very, very far apart, and there's this length of conductive wire connecting them. Now, some people are going to argue at higher up levels that, okay, if they're close enough together to interfere with each other, and you take two spheres and you touch them together, then this wouldn't be true. That's correct. But right now, AP Physics 2, this is going to work out for us. So, looking at this, if we wanted to solve out and talk about the charges involved, remember the original charge was this big Q, and we're going to have Q1 and Q2 summing up to the original charge, big Q. Okay. If we look over here, I have Q1 over R, Q2 over little r. I know I don't have numbers right now. Let's go ahead and give it some numbers. So let's call R over here 1 meter. Let's call the R over here half that, 0.5 meters. And let's plop down about 10 coulombs of charge on this big guy. And so we're going to have 10 coulombs of charge equaling Q1 plus Q2. We're going to have R, big R, be 1, and we're going to have little r, that's going to be 0.5. And we're also going to have Q1 and Q2 as unknowns. Well, we're kind of stuck at the moment unless you realize that we do have 1, 2 unknowns, but we have 1, 2 unknowns over here. This is a system of equations. And so if I want to, I can move, let's say I'll move the Q2 over. So I've got 10 minus Q2 should be equal to Q1. Q1, we're going to pop that in right there because there's a 1 on the bottom. That's convenient. So 10 minus Q2 should equal Q1. That's what we just plugged in. That's what we substituted in. And Q2 on top. And there should be a 0.5 on the bottom. Let's go ahead and multiply everything by 0.5. Move that over. So 0.5 times 10 is going to be 5. 5 minus 0.5 Q2 is equal to Q2 itself. I'm going to move that over. 5 is equal to 1.5 Q2. And then we're going to divide and say 5 divided by 1.5. What is that going to be? 5 divided by 1.5. I should already know this. 3.33333. That makes sense. So Q2 should be about 3.33 repeating coulombs of charge, which makes Q1, if you do Q2 right there, so 10 minus that is going to be 6.66666 charge. So Q1 equals 6.6666 repeating coulombs of charge. Okay, so what happened here was that the bigger sphere did end up with more charge. It's bigger, they can spread out more. The little sphere ended up with less charge. The next question that I would have is, all right, they're at equal voltage. They don't have equal charge. This one has more charge, but it's bigger. This one has less charge, but it's smaller. Who has a stronger electric field at the surface? So take a guess. Who would have the stronger electric field at the surface? The one with more charge, that's bigger, or the one with small charge, that's, well, smaller? And the answer, considering that we did connect them and they're at the same voltage, would be found by looking at our electric field equation. So let's look at our electric field equation. And so we're going to say the electric field for the left one is going to be 9 times 10 to the 9th. All right, that's K value. Q1, it's going to be 6.66 coulombs of charge divided by the radius, which is 1, and we're going to square it. So that's KQ over R squared. Looking at the electric field for object 2 over here, the right side, we're going to have that same 9 times 10 to the 9th. We're going to have 3.33, okay? And that's going to be divided by KQ over R squared. So R squared is going to be 0.5 squared. And so I'm looking at these two. Really, I don't really care about the 9 times 10 to the ninth because that affects both the same way. I'm going to notice that I have the 6.66 over here. And so I want to find out what 3.33 divided by 0.5 squared is. And what that is going to be 13.32. So on the left side, I've got this K value times 6.66, which is going to be my electric field for this bigger object. For E2, the smaller object, that's going to be this K value, 9 times 10 to the ninth, times 13.32. So it turns out that although the smaller one has less charge, that size difference being half the size, that gave it a much larger electric field value. Okay, like twice the amount. So considering that, looking at electrodynamics, that's going to be your two conductive spheres that one's charged, one's uncharged. We touch them with this metal wire. The voltages become the same. Remember, the voltage is like the push that's trying to push back and forth, this energy that's about to be there considering the charge that is affected by it. And we find that the electric field for the small one's going to be more, even though the charge is bigger on the big guy.